groundbreaking technology.
With countless applications.
Creating a new level of speed never seen before. It may not look very exciting, but magnetic printing has a lot of potential applications.
We're Attractive Printing, here to show off our magnetic printer. My name is Jeremy Spencer.
I'm Adam Farger.
And I'm April Fisher.
In this video, we're going to tell you what makes this printer a magnetic printer, some of the benefits that could come from this project, and show a demonstration. We'll also explain the inner workings of the device and give the results we found.
What does make this printer a magnetic printer? Well, instead of text or pictures, this printer prints electronic components. Its unique ink has tiny metal particles.
While in the printer, the particles are randomly oriented, but putting them through a magnetic field will force them to align the same way.
Why create a magnetic printer? This amazing technology can be used to optimize the performance of antenna and on-chip inductors and open up possibilities for other magnetic devices that would not be feasible otherwise.
With this device, we can print any arbitrary shape and alignment with a defined resolution as small as 100 micrometers. Next, we'll look at all the components that make up our magnetic printer and how they work. This is the block diagram for our entire system. We'll be walking you through each block and explaining how they work, as well as listing off some of the engineering requirements associated with that block. Let's start with the TIPS controller. Engineering requirement number 1. The magnetic printer will utilize a single solution of UV cure and magnetic ink to print. HP's thermal inkjet PicoJet system is a research tool that was donated by HP. These are currently being used in some pretty amazing applications, from dispensing medicine to printing body organs. It consists of a single computer programmable controller and a tip that acts as both reservoir and nozzle. With this, we can print almost any viscous fluid. Engineering requirement number 2. A single desktop computer running LabVIEW will be able to control the variable functions relating to the magnetic field strength and direction, print dimension, and XY stage settings. The user interface is available to specify every physical parameter of the device that would be printed. The user provides 2 files, one containing the alignment direction and the other the magnitude of the alignment. They will then adjust the resolution and number of layers to print. The purpose of the UV Cure LED is to quickly cure the ink after it contacts the substrate. This will allow every drop printed to have a unique alignment and also gives us the ability to stack up layers of ink to print 3D structures.
Engineering requirement number 3. The system will have a moving substrate no greater than the dimensions of the stage, 10 centimeters by 10 centimeters, which moves while the fluid printer head is stationary. The stage, a 10 centimeter by 10 centimeter piece of aluminum, is the only moving part of the whole assembly. A substrate, such as photo paper or a transparency, is taped to the top of it. While the TIPS printer is releasing ink through the magnetic field, the stage is programmed with LabVIEW software to move to any location to create whatever shape the user wants. The stage is mounted on 2 rails, one enabling X direction movement and the other Y direction movement. As an added feature, on each rail there are 3 Hall effect sensors. The home sensor in the middle of each rail is meant to center the stage, and the Hall effect sensors on both ends of each rail are meant to keep the stage from passing those points. In order to move the stage, the rails each have a stepper motor built in. These stepper motors are controlled by 2 Microlinks controllers. As you can guess, one of the controllers is for the X direction and one is for the Y direction. The controller's job is to communicate LabVIEW commands to the stepper motor controllers, which then move the stage. The controllers also take in information from the sensors and communicate location status back to LabVIEW.
The printer frame and enclosure provides physical structures for the integrated system parts. The frame, which supports the thermal inkjet and printing stage, is constructed of 30 centimeter by 30 centimeter plate steel, 3 30 centimeter long aluminum beams, and aluminum braces and fasteners. The enclosure, which secures the microcontrollers, stage power supply, and wiring, is a prefabricated plastic electronics box with custom drilled mount holes. The stage power supply provides 24 volts DC and 3 amps max to the 2 motor controllers. It is a prefabricated power circuit that plugs directly into any 120 volts AC wall outlet and additionally has been fitted with a simple on-off switch. The mag power supply, controlled by the lab computer, provides up to 10 amps bipolar current to the magnetic field alignment device. Bipolar means current in a wire can flow in either direction. The OSU Magnetics Lab allowed us to use 2 bipolar power supplies.
Engineering requirement number 4. The magnetic field alignment device must be able to supply a 10 millitesla magnetic field strength. Engineering requirement number 5. The magnetic field alignment device must be able to direct the magnetic field 360 degrees, plus or minus 10 degrees tolerance. The purpose of the magnetic field alignment device is to orient the magnetic particles, as was shown before. The device is a picture frame design, meaning there is a frame of metal called the core, and 4 fingers that go into the center, where the TIPS printer dispenses the magnetic ink. There is a shield that surrounds the tip of the printer so that the ink is not aligned before it exits the printer. The shield, fingers, and core are made from mu-metal, which is a special kind of metal that has a high permeability. Permeability is the ability of a material to become magnetized after being introduced to a magnetic field. There are 4 coils of wire wrapped around the 4 sides of the core. The coils parallel to each other are connected by 1 wire. This means the same current runs through them. Each set of coils induces a magnetic field and controls either the X or Y direction. Turning on one set of coils sends a magnetic field down the fingers and orients the magnetic particles of the ink in the X direction. Switching the polarity of the current sends the magnetic field in the opposite direction. Likewise, the coils controlling the Y-axis send the magnetic field through the fingers and along the Y-axis. So what happens when the coils are all on at the same time? If the magnetic field induced by all the coils is equal, then the field will come out at a 45-degree angle. Varying the polarity and magnitude of the current can therefore result in any angle.
Here's an aligned sample we created with the magnetic printer. To test its magnetic properties, we put it in the vibrating sample magnometer. The VSM measures the magnetic alignment of a sample. By measuring the aligned axis as well as the axis perpendicular to it, we can see that there's a clear alignment of the sample. We can see that on the axis of alignment, the magnetization switches faster. This can also be stated as the permeability of the device at higher frequencies has increased.
As previously stated, the LabVIEW interface allows us to print any arbitrary shape that we define in a simple matrix.
Earlier this year, the OSU Magnetics Lab published a paper in the Journal of Applied Physics. Click here to view that paper.
Before we close, we'd like to thank our supporters and donors: Hewlett-Packard, Magnetic Shields Limited, and the Oregon State Magnetics Lab, as well as a special thank you to Han Song and Colby Whitaker for their support and advice.
We've shown how this groundbreaking technology implements a thermal inkjet printer, magnetic ink, and a magnetic field to print magnetically aligned components, some which would not be feasible otherwise.
For more information about our project, click this link to view our website. Thank you so much for watching.